Good evening, everybody. Today is day 18 of Math 133, and we're going to be talking about the Chapter 8 review, which starts on page 471 in your course pack, page 471. Um, let's see. Uh, for the lecture notes, it's just 9.1. Um, so, we've gone through a lot of material so far, and some of the material we've gone through very quickly. I feel like sometimes it's like we just blaze through it. But chapter 9, we're going to try to go a little slower because some people struggle with chapter 9. So uh, it's about confidence intervals, which might be something you haven't dealt with before. So you'll notice that chapter 9, we're doing starting the lecture notes now, but we're not going to do the review until like a week and a half later, or 2 weeks. Yeah, a week and a half. So, um, anyway, so we're going to go through and make sure everybody understands what we're doing with chapter 9, okay? Um, all right, and then Tuesday we have our candy project. So you want to make sure that you've got some M&Ms and some Skittles. So 3 ounces or more of M&Ms and Skittles. Bring those to class on Tuesday. Okay. We're going to be using the data that we collect from those for the Chapter 9 project and the Chapter 10 project and the Chapter 11 project. So it's important data. We're going to keep using it. Okay. Um, but I think that's it. So, uh, yeah, we're doing the whole review today. Page 471. Okay. So just like any of our worksheets, I'll give you some hints, skip over some of the ones that I think are a little easier, and then we'll go back and we'll make sure we fill in all the answers. Okay. So question number one, fill in the table with the appropriate symbols from the list. So we're going to be talking for the rest of the class about populations and samples. I mean, we've been talking about populations and samples already, and there's different symbols for those. But I'm going to skip this one because you guys probably know all the answers on that. Um, question number two, you can find information on this on page 183 in your course pack. Okay. Um, yeah, so uh the one that let's see, I'm gonna skip through that. Yeah. Um, the one I actually want to look at is on the next page, page 472, number 3. Um, so this one, you'll find information on this on page 184. Okay. And page 184 is about the central limit theorem for means. Okay. So I'm actually going to pull up the course pack for this. So here it is, page 184, central limit theorem for means. Okay. This is a very important theorem in statistics. I mean, it's the central, it's a big deal, right? So we're going to be using it for the rest of the class. Okay. Um, so just like with any theorem, there's certain conditions that you need to meet. The theorem that you guys are probably the most familiar with is the Pythagorean theorem. Pythagorean theorem is in geometry class, and it's a squared plus b squared equals c squared. And it's an important theorem that's, it's been around for thousands of years, but we use it in geometry for a ton of stuff. Okay. It's actually also used in trigonometry and it's kind of a big deal. But it only applies under certain conditions. It only applies if you have a right triangle. Okay. If you don't have a right triangle, then you can't use a squared plus b squared equals c squared. Okay. So just like that, the central limit theorem has requirements that need to be met as well. So the Pythagorean theorem, it's just one condition. It has to be a right triangle. But for the central limit theorem, there's three conditions. Okay. It needs to be random, independent, and normal. Okay. We'll come back and we'll talk more about those. We're going to be talking about those throughout the entire class. Okay. But the thing I want to point out for the central limit theorem is if you satisfy those conditions, then the distribution of sample means will be normal. And that's what we found out on Tuesday was uh, it doesn't matter what your original population was. It can be skewed left, it can be skewed right, doesn't matter. Your distribution of sample means will be approximately normal. Okay, which means we can use all the things that we learned in chapter 7 about the normal curve for uh, the rest of the class when we go into chapter 9, chapter 10, chapter 11. We're looking at confidence intervals and hypothesis testing. This theorem is going to allow us to use the normal curve. Okay. The center of your sampling distribution is just the mean of the population, okay, which basically means that the samples that you take will have a mean that is a good representation of your population mean, okay? That's why we can take a sample and why why we don't have to just, measure everyone, okay? But for question number 3, the thing that I need is this formula down here. This is the standard error. This is the spread of the sampling distribution. And the formula is right here. It's SEX bar. I don't know if that helps you memorize it, but SEX bar. And uh, all of this is confusing. Really what it is it's the standard deviation divided by the square root of your sample size. So I'm going to write this on page 472, question number 3. So SEX bar is S divided by the square root of N. Okay. Now this formula is not on your exam notes packet, your yellow packet. Okay. So it's going to be one that you're going to want to make sure you have written down on your 8.5 by 11 piece of paper. Okay. I mean, you can write on the exam notes packet. I'm okay with that if you want to write it on there, but it's not on there right now. Okay. So unless you plan on memorizing this one, yeah. So but this is how you calculate the standard error of the sample mean. Okay. Standard error of the sample mean. All right. All right, moving on. Question number 4. The average BMI for adults in the US is this. Standard deviation is this. A weight loss researcher gathers a sample of 72 random US adults, 250 million US adults, adults in the US. Okay. Verify the conditions of the central limit theorem for means are met. Okay. So a second ago, we said that the conditions, there were 3 of them. We need to check that it's random. We need to check that it's independent. And you can do these in any order. This is just the order that we're going to be doing them. Just, I don't know, it helps memorize it. So you don't have to do them specifically in this order. Okay. But um, random, independent, and normal. So let's jump back over here and let's take a look at these again. So in order to use the central limit theorem, in order to say, okay, our sample distribution of means is a normal shape, which is, a very interesting and surprising result. We have to make sure that we're satisfying these conditions, though. Okay. The condition that we talked about on Tuesday was the normal one. So our sample size had to be 30 or larger, right? 30 in our Chapter 8 project was kind of the magic number where it stopped being skewed and it started appearing more and more symmetric, right? So, but let's start with condition 1. Like I said, you can do these in any order, but let's start with random. So, each observation is collected randomly from the population, okay? So, what does that mean? It means that, if I'm trying to measure something, like let's say I'm trying to measure uh what's the average height of everyone in the US? I can't measure that, okay? Because there's hundreds of millions of people. I can't measure everyone's height and then take the average, okay? Um, that would take too long and it'd be too expensive. So instead, what I can do is I can take a sample and I can measure the height of, let's say we do like 1,000 people. That's going to still could take a little while to do, right? But it's not going to take forever. So I'll get 1,000 random people, I'll measure their heights, and then average those numbers. And the number that I get, that average, that sample mean, is going to be very close to the actual population average, the actual average height of all the people in the US, okay? And that's why we are going to be taking samples, and that's why we can use samples because of what, this central limit theorem is saying, okay? But it does say that you have to make sure that you're selecting your sample randomly. That means that every single person in that population has equal chance of getting selected. That's actually difficult to do. Okay. In class, in our class, that's going to be the easiest one to check. Okay. So for class, all I have to do is look at my word problem and say, is the word random somewhere in there? Yes, it is. There it is. So yes, given, right? Done. Okay. But in practice, this is actually the hardest condition to satisfy because in order, think about it like this. If I wanted to measure 1,000 people's height in the US and I wanted to, take those 1,000 people and then average those heights, every person has to have equal chance of getting selected. So that means when I, select my 1,000 people, I'm going to end up getting people from all over the place. I'm going to get some people in California and some people out in Alaska and some people in Florida. I'm going to have to measure those heights, which means like, am I going to have to travel all over the place, and then knock on those people's doors and ask them like, hey, can I measure your height? Like people are going to say no, like I go away, right? So it's going to make it difficult to do a random sample. So there's other things you can do. You can do like a stratified sample. You can do, we've talked about different sampling methods, right? But we've also talked about biases that can come up because if your sample is not random enough, okay? Um, so let's say instead, like let's say I actually wanted to do something more useful. Let's say I wanted to figure out who's going to win the next presidential election, right? So um, when the presidential election year comes up, you can't go and ask every single person how they're going to vote. Okay, that's going to take too long and it's going to be impossible, right? So instead, you can do what's called a poll, and that's what all of the news reporting is based on. Is based on polls where they asked a couple people in a sample, right? They maybe they asked 100 people or 1,000 people how they were going to vote, and they use that as a prediction for the entire population. Okay. So if you do that, uh, you still need to make sure that your sample is random. Okay. Well, you can't, like I said, you can't necessarily just pick 1,000 random people because then you're still going to have to contact people from all over the map, right? And so instead, maybe you select people from a certain area. Well, that's still not going to be good because that's going to be biased, right? So if I, only ask people in California, okay, my prediction is going to be wrong. My prediction is going to say that it's the whoever the Democratic candidate is, they're going to win by a landslide because California is a well-known blue state. Their electoral votes almost are always are going to the Democratic candidate. On the other hand, if I asked, people in Alabama who is going to win the next election, who they're going to vote for, I'm going to say, oh, well, it's clearly the Republican because Alabama is a well-known red state. Okay. And so you introduce bias by not selecting a random sample. Random meaning every person has equal chance of being selected for your sample. Okay. Anyway, I'm going off on a tangent. I apologize. For our class, though, the random part is the easiest, but I do want to just point out that, like, don't let that fool you. Random is actually very difficult to do. The next one is independent. Independent, we just have to make sure our sample is not too big, and that's the easiest one. That's just be a little more lazy, right? Don't sample too much. Okay. And usually that's not a problem at all. Okay. But to measure this, you need to make sure that your sample size is less than 5% of the population size. That's what this formula here is saying. Now, if you multiply both sides of this equation or this inequality by 20, you get 20n is less than 20 times 5%. 5% of 20 is 1. So you get 1n. So it's easier to do it this way. The population must be at least 20 times larger than the sample size. So the formula that I'm going to write for independent is 20n is less than n. 20 times the sample size is less than the population size. Okay. This and this are the same formula. You can use either one. Okay. And I might switch back and forth between the two every so often, but for now, I'm going to use this one. Okay. So 20 times n. What is my sample size for question number 4? What's my lowercase n? Gary says 250. You guys agree? Same answer, different answer? What's my sample size? Crystal says 72. My sample size is 72. Okay. Um, this is the people that I randomly selected. Random sample. Okay. 72 random US adults. What's my population size? What's my capital N here? That's the 250 million. Okay. That's everybody. Somebody do in your calculator 20 times 72 for me, please. Yeah, that's okay, Gabby. No big deal. 20 times 72 is, what year is it? 1440. Okay. So, in order to satisfy the independent condition, um, is 1440, is that less than 250 million? Yes, it's way less, right? Yes, of course, right? This is usually not a problem. Checking independent is usually pretty easy because your sample is going to be way smaller than 5% of the population. If what is 5% of 250 million? 5% of 250 million would be, let's see, it'd be 5 million. If you have the resources to go and measure the BMI for 5 million people, okay, um, then actually, no, I did my math wrong. It's 12.5 million. 12.5 million people. Like at that point, you can just measure everyone. Okay. Um, the whole point of doing a sample is your population is too big to measure everyone. So we do a sample, which is much easier, much smaller. So your sample size is always going to be tiny compared to your population size. Okay. So this one's usually not a problem. Okay. Now I will point out that this formula here, 20n or n is less than 5%, is not the exact same formula that you will see when you look at the central limit theorem on like Google, or if you're using some kind of AI, which you're not supposed to be using. So this one is a little more strict. Okay. It's going to end up with better results if you do this. The one that they say is like you can go with it up to 10%. But like I said, you're never going to do that because the whole point of taking a sample is you can't measure so many people. Okay. So 5%, 10%, those are way out there. Okay. But I will say that if you're using the formula, if you're not using the one from the class, if you're make sure you're using this one. If you're using the one that you find on, Wikipedia, you're going to end up losing points. Okay. So this is a good one to write down also on your exam notes packet um, when you're checking independent. Now, the last one is normal, okay? So let's see where it is. in order for it to be normal, there's two ways you can do it. The first is if your population is normal. We saw that, like, if you build like a quantile chart, you can tell if it's normal. Um, yeah, that's fine. But we also saw on the Chapter 8 project that once you have a sample size that's big enough, once you hit 30, that distribution starts to turn normal, right? And so 30 is kind of the magic number. So really what we need to check here is we need to check that n is bigger than 30. So n, where is my thing? Here it is. N is greater than 30. We said that our n was 72. So is 72 greater than 30? Yes. Okay. Now, that gives us three yeses. So if you have three yeses, then we're good. That means the central limit theorem applies, and we can use all of its superpowers, which is that the distribution of sample means will be normal, the center will match up with the population mean, and the spread is the standard error formula down here. Okay. Um, Now, I will point out that in the central limit theorem, they're using less than or equal and greater than or equal. I didn't include the equal here. So if you want to include the equal, you can. So if your sample size is 30, technically you are matching the central limit theorem. So if your sample size was 30, 30 is greater than or equal to 30. But 30 is the lowest limit. And I'm going to be saying this throughout the entire class. The bigger your sample size is, the more accurate your results will be. Okay. Um, so 30 is still too small of a sample size. Okay. 30 is still terrible. Um, you really want to have a sample size that's somewhere around like 100 or 1,000. Okay. Those are reasonable sample sizes. So I'm going to be kind of ignoring the less than or equal to. I'm going to be ignoring the equal to part, but technically it's there. So if you want to write it as, you know, 20n is less than or equal to capital N, then that's fine. But like I said, you're never going to sample 12.5 million people. That's too big a sample size. You should not be using a sample size of 30. That's really too small a sample size. Okay. So anyway, um, so that is for means. Okay. We'll be talking about proportions in a little bit. Okay. So proportions is going to be very similar, but not exactly the same. Here we are talking about averages or means. So we are using page 184 for that. Okay. All right. So now that we've got that, we can describe the shape and the center and the spread of our sample distribution. So shape, center, and spread. Okay. The shape is normal. Okay. And that is the part that is the important part of the central limit theorem. But the center is also an important piece. The center is this crazy thing. Um, so this is just confusing. So
Hey,
this
Mike.
symbol. Oh, go ahead,
Amanda.
Gabby.
I have a question because on our worksheets we did yesterday, we did the random independent and the normal, but we
Yes.
also did m times p times q greater than equal to, and then 10, and then we did the times, and then we did the uh
We did, and we will be talking about that, but that's for proportions. So I guess I could ask this. What's P in this case?
um,
Well, there isn't a P. This isn't measuring proportions. This is measuring averages. Okay.
okay.
So um, this is measuring means, right? So we will be talking about, so wait, you're jumping ahead on me a little bit.
Oh, I'm
Uh,
sorry. Sorry.
So we'll be talking about proportions when we get to the next page, and also the last page. So page 189
Okay.
in your course pack is the central limit theorem for proportions. Okay. Now they are very similar, but there are some slight differences. And so it's going to be important that you pay attention to, are we measuring means here or are we measuring proportions?
Yeah.
And um, I've already started confusing the two. Okay, because I mentioned two examples earlier. I mentioned if you wanted to measure the average height of everyone in the US, and I mentioned if you wanted to figure out who is going to win the next presidential election. Those are not the same. If I asked you how tall you were, if I, let's say I want to measure the average height of everybody, and I go and I measure 1,000 people. If I ask you how tall you are, what's your answer going to be? Your answer is going to be a number. Your answer is going to be, I'm 5'7". Your answer is going to be a quantitative number. And then we can take those numbers, add them all up, divide by the number of numbers that there are, and we get a mean. Okay. If I asked you who you're going to vote for in the next presidential election, your answer is not a number. Your answer is going to be, oh, I'm going to vote Democrat, or I'm going to vote Republican for the Republican candidate, or maybe the independent one, right? Or I'm not even going to vote. But your answer is not a number. So I can't take you all of those people in the sample and add them up. I can't add up all the thousand the Democrats and the Republicans. That doesn't make any sense. When your answer is a qualitative result, which is what that would be. It's a word. Qualitative results, we talk about proportions. Okay. So we'll talk about that in a little bit.
How do you tell?
So,
I just want to ask, how do you tell the difference? Like
well, first of
from
all,
that
if you
confusion
see
that's
the
on the
word
final.
average or you see the word mean or see the word proportion in the question, then it becomes obvious, okay, we are talking about the central limit theorem for means. Or if I see the word percent or proportion, I would be talking about the central limit theorem for proportions. Another thing you can do is you can look at it as, well, if let's, what would the answer be for someone in that sample? If I measured someone's BMI, would I get a qualitative result or would I get a quantitative result? I would get a quantitative number. BMI is measuring your uh, kilogram per m squared, which is a number. Okay. And like I said, we will be looking at both means and proportions today, but we're also going to be looking at means and proportions throughout the rest of the class. And so by the end, by the time the final gets here, you're going to be like, oh yeah, I can tell which one's mean, which one's proportion. So I know right now it might be confusing, but you are yeah, you don't need to worry about it. Okay. So, okay. So there's all of that. So let's go back to what we were talking about a second ago. So, uh, the other thing is right here, describe the sampling distribution of the sample mean. I have the word mean, so it's clear that I'm using page 184. Okay. Now, this symbol that they write on page 184 is just crazy confusing to me. It says mu sub x bar. That's how you read that. What it means is it is the mean of the distribution of sample means. What the heck does that mean? All that means is that your mean of the distribution is the mean of the population. Okay. Well, that's still confusing. What this tells us is that when you take a sample that satisfies the conditions of the central limit theorem, then your samples will be a good representation of the mean of the population. Okay. I don't need to measure everyone's BMI because I can't. If I want to get what is the average BMI for all the adults in the US, I can measure a reasonably large sample and get very close, extremely close to what the true population mean is. Is the true population mean 30.7? No. This is the sample mean, but maybe it's 30.8, maybe it's 31, maybe it's 30. but we're close enough that we can be sure that the medicine that we're building or the medicine that we're creating like is going to be valuable. Okay. So all you have to do here is we just write out what the center is. So what was the mean? The mean was 30.7 kilograms per m squared. Okay. And you don't even necessarily need to write this. You can just say, the center is the mean. Okay. If you find this mu sub x bar thing confusing. Okay. Lastly, the spread. So the spread of the sampling distribution, that one's actually a little bit of work. That's actually a formula. That's our SE x bar formula. SEX equals S over the square root of N. Now, like I said before, this has like a whole bunch of stuff to it. Don't write all of this on your exam notes packet or on your 8.5 by 11 piece of paper. Just write this one, okay? SEX XES bar equals S over square root of N, okay? All of this other stuff is saying standard deviation by the square root of the sample size. Sometimes you might have the population standard deviation. Sometimes you have the sample standard deviation. You're never going to have both, okay? So we just write down whatever the samples, or sorry, whatever the standard deviation they gave you is. Here they gave me 6.1 as the standard deviation. We said the sample size was 72. So let's type that in our calculator, see what we get. 6.1 divided by the square root of 72. To do a square root in Desmos, you do SQRT. Squirt. 72. And we get 0.714 decimal places. 89 units, kilograms per meter squared. Okay. All right. All right. Let's move on to page 473. Okay. Page 473, we have following just three distributions are the sampling distribution of sample proportions. All right, they said the word proportion, which means we are not using the sample, the central limit theorem for means. We're using page 189, which is the central limit theorem for proportions. Okay. That's the only hint I'm going to give you on this page. Let's go to the next page. Page 474. So on page 474, we have 189. N is this, P is this, assume a random independent sample, blah, 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 compute SEP hat. So here, page 189, I'll pull it up in the course pack, is the central limit theorem for portions. Where is it? Here it is. Okay. Now, it's very similar to the central limit theorem for means. Okay. There's just a couple of small differences. Okay. So why do we have two separate ones? Well, because sometimes we're talking about means and sometimes we're talking about proportions. I gave you an example earlier where we wanted to measure the average height of everyone, or we wanted to measure who's going to win the next election. Okay. Those are one's a mean, one's a proportion. Okay. But they're very similar. So instead of having them in two separate chapters where we cover the means and then we come back to a different chapter and do the proportions, we're going to put them together in the same chapter. And we're going to do the same thing in chapter 9. Sometimes we'll be talking about means, sometimes talking about proportions. So, I mean, that way you don't have to learn it and then learn it again. Okay. Um, you know, we could put them in two separate classes where this class is just about means, the next one's about proportions, but instead you get two classes in one. Okay. So most of it's the same. Uh, so there's two minor differences. One of the differences is the spread, the standard error of the proportion, is this crazy formula. Okay, it is the square root of p q over n. Now there's two of them there. There's pq over n and the p hat q hat over n. Okay. How do I tell which one to use? Well, you're never going to have both. Okay. So if they give you p, use p. If they give you p hat, use p hat. You're never going to have both because if you have the population proportion, there's no point in taking a sample. Okay. So there's no point in calculating p hat because you already know what p is, okay? So anyway, so this is another formula that is not on your exam notes packet. So another one that you're probably going to want to write down on your 8.5 by 11 piece of paper, okay? Now this formula, by the way, is actually the same formula as standard error of x bar, standard deviation over square root of n, because the standard deviation of the proportion is square root of p times q. So technically they are the same formula, but they don't look the same. So we're going to write them out separately, and you probably want to make sure you have both written on your exam notes packet, even though, they are actually related. So. Uh, okay. It's kind of like how, you know, these two formulas are related, but they don't look the same. You have to do some math to get from one to the other. So maybe it's better to just know both of them, right? So, okay. So question 7, a study found 39.5% of US teens have their driver's license. A random sample of 224 US teens is taken. Verify that the conditions of the central limit theorem for proportions are met. So we still need to check and make sure that the sample is random, it is independent, and it is normal, okay? And then if we get 3 yeses, then that means that the central limit theorem is satisfied and we are able to then talk about the shape of the sampling distribution. We're going to talk about the center and the spread. Okay. By the way, this one's not done yet. I just wrote out the formula. Okay. So you have to go back and finish doing that. But for now, that's all the hints for today. I'm going to stop the recording and we'll go back and answer what we skipped.